Let us start with from the last lecture. Last lecture we started the graphical solution of LPP consisting of two decision variables only in the objective function. We have talked about two things. One is the search method, another one is the Isoprofit method. So, let us see how it works. Let us take this example. Maximize z equals x1 plus 3x2 subject to 3x1 plus 6 x2 less than equals 8 and 5x1 plus 2x2 less than equals 10, x1 x2 greater than equals 0. So, first let us do this problem using the search method, then we will see the same problem with the Isoprofit method. In the search method, first what we have told, you convert this inequation into equation, that is this we will write it as 3x1 plus 6x2, this is equals 8, and the second one will be 5x1 plus 2x2 equals 10. So, that now there are two lines and these two lines we can draw very easily. Suppose this is your axes x1 and x2. So, this goes to 0 and 1. Suppose we are assuming this is 1, 2, 3, 4 and 5. Similarly, on this side also 1, 2, 3, 4 and this is 5 say. So, the first line whatever you see 3x1 plus 6x2 this is equals x. This can be written in the form of x1 by 8 by 3 plus x2 by 4 by 3. This is equals 1. So, that the intercepts on x1 and x2 are 8 by 3 and 4 by 3 respectively. So, that the drawing becomes much easier. So, one line will go through just below 3 here and the point 2, that is it will be something like this, and there will be another line which is going through 5 and 2, that is it is something like this. So, your 5 and 2 is the line 2, if this is the line 2, if this is the line 1. So, this represents the line 2, whereas this represents the line 1. So, first what you are doing, you are just writing the equalities 3x1 plus 6x2 equals 8 and 5x1 plus 2x2 equals 10. This you can write down in standard intercept format. Second one you can write down x1 by 2 plus x2 by 5, this is equals 1 also. From there you are drawing two lines, this is the line 1 and this one is the line 2. Line 2 is going from 2 0 and it is intercepting at 0 5. So, what is happening? Once you are drawing this one, your feasible region becomes the intersection of these two lines x1 axis and x2 axis on the positive side. That means, on this side only the lines bounded by these four lines, this line 1, line 2, x1 axis and x2 axis, or we can say that the feasible region is this thing. So, first what you have to do, this was the step 1. In step 2, you have to find out the extreme points. As you remember, your extreme points are which one? The boundary points, that means the boundary intersection of two lines. So, one is this point 0, that is 0 0. Second one we are saying this is a point A, say this is the point A. So, point A the coordinate is 2 0, already we have done it 2 0. Then if I see this is the point B. So, your point B, if you calculate from here by solving, you will get 11 by 6 and 5 by 12. And the last point is this one, because this is the feasible region. From 0 to I am going like this, then from here and coming back to this. So, the last intersection point or extreme point is the point C. Again C is x1 0 and x2 will be, actually it is not 2, it is little less than 2, 2 will be sometimes here, it will be 0 and 4 by 3. So, these are, you see, these are the extreme points. So, what you are doing? Please note this thing. This is the extreme points. So, first you are getting the equations. From the equations, you are writing it in the standard intercept form. You are drawing the lines. Once you have drawn the lines, after that, from there you are finding out 0, A, B, C, the extreme points. Now, at each extreme point, what is the value of the objective function z equals x1 plus 3x2, that you have to find out now, which becomes easy. So, at the point 0, 0, the value is 0, your ZA, if you calculate, it will become 2, your ZB, this will become 37 by 12, and your ZC, this will become 4. So, from here it is quite clear that the optimum is attained at the extreme point 0 and 4 by 3. So, therefore, your Z max is the value is 4 and Z max equals ZC, and this is equals 4, and the corresponding vertex is 0, 4 by 3. So, the solution of your problem by using the graphical method is at the extreme point 0, 4 by 3, you will obtain the optimum value, that is maximum value in that case, and maximum value of the objective function is 4. I hope it is clear. I am repeating once more the steps. The first steps are, first step is first convert the inequality into equation type. Then for each equation draw a line on the x1 x2 axis, just we have drawn the lines 1 and line 2. And once you are drawing the line, you find out what is the feasible region. Feasible region is intersection of the equation lines, whatever you have drawn from the constants, and the x1 axis. This is your x1 axis here, this is your x2 axis here, and then find out the extreme points, that is intersection of these 4 lines. For this case, you got it O, A, B and C. So, these are the 4 points. At these 4 points, you find out what is the value of the objective function z, which you derived like this, and from there whatever is the maximum value of z, that extreme point gives you the optimum value. So, therefore, optimum value can be obtained at 0, 4 by 3, and the optimum or maximum value of the function is equals to 4. Now, let us see how we can solve the same problem using Isoprofit approach. So, next one is Isoprofit approach. In Isoprofit approach, as I mentioned earlier, the first 2 steps are same, that is the same figure you draw, and from the same figure you find out what are the extreme points. So, I am just drawing once more the figure. This is your x1, this is your x2. So, say this is your 3, somewhere here you have the point 2, here it is say 2. So, just below 2 one point will come, it is something like this, and there will be another point. If it is 5, then 2 and 5. So, it will be something like this. So, this was your 0, this is your A, this is your B, this is your C, and already you know what is the feasible region. Now, you have to draw a profit curve for some value of z such that the profit curve lies in the feasible region. Your function is z equals x1 plus 3 x2. I am assuming my profit curve initially is z equals 1. Z equals 1 means if here it is 2, it is 1 say. So, it will be something like this. So, this is your profit curve. This one is the profit curve for z equals 1. This value z equals k, basically it is z equals k can take any arbitrary value. This we have taken arbitrarily in such a manner that whenever I draw the line z equals 1 or x1 plus 3 x2 equals 1, that line lies, portion of the line lies in the feasible region. Your next step is you move this line z equals 1 away from the origin by changing the value of k, such that whenever it goes to maximum distance, it gives the value as a maximum value for z. So, from here it is quite clear, if you move in this direction, if you move along this line, then it will be at some point of time I will get some line like this. So, which basically crosses the point C. So, once it is crossing the point C, that is C is your 0 4 by 3, there you will obtain the maximum value, that is z max equals z c, and whose value is equals to 4. So, the basic idea is move the line away from the origin, so that your profit becomes optimum, and at some boundary point it will cut where you will get the maximum value of z. For this particular problem, you are obtaining the maximum value of z at the point C. Therefore, your optimum value remains the same. So, this is the isoprofit approach. Similarly, if you want to use the iso minimum approach, that is for minimization problem, this profit curve should move towards 0. Please note this one. For maximization problem, the profit curve should move away from 0, whereas for profit curve for minimization problem should be at the towards the origin, so that you can obtain the minimum value of z. So, I hope it is little bit clear to you. Let us take one more problem in this direction, so that it becomes easy for us. The next problem, let us take maximize z equals x1 plus x2 subject to x1 plus x2 less than equals 1, minus 3 x1 plus x2 greater than equals 3, and obviously x1 x2 greater than equals 0. These are the three conditions whatever you are using. So, I am not writing this one. First, you have to write down x1 plus x2 equals 1, and minus 3 x1 plus x2 equals 3, and after that you have to draw the lines. So, I am just directly drawing the curve over here. So, this is the point 0, there will be a point 1 0 for the first one, there will be another point, that is 0 1. So, you will get the line like this. So, effectively this is x1 plus x2 less than equals 1, that means its direction will be towards the left hand side of this line, towards the downward side. So, x1 plus x2 this is equals 1. This arrow indicates that the region will be on this side below this one, since it is less than equals 1. Because here if you note that in the constant we have one less than equals constant, we have another greater than equals constant. So, for less than equals it will be below the line, whereas for greater than equals the region will be above the line. For the other one it will be, I think one is minus 1 say, and the other point will be say 3. So, that the line will be something like this. This is the minus 1 point, this is the point 3. So, this line is your line is x 1 minus 3 x 1 plus x 2, this is equals to 3. So, it is going in this direction. So, if you think about this one is going like this, another is going like this. So, the feasible set, that is the intersection of these two lines and the positive x axis and y axis, that is positive x 1 and x 2 is empty. So, here the feasible set, if I have to say, this feasible set is empty. Please note this one, because there is no intersection point. One portion is this side, another portion is this side. There is no common portion. So, feasible set is empty, and once feasible set is empty means, as you know, the solution whatever will be there, which will satisfy the constraint and the non-negativity condition, always must lie in the feasible region. But and the feasible region is equals to the intersection of the lines and the x 1 axis and x 2 axis on the positive direction. So, therefore, for this case the feasible region, there is no feasible region, or we are writing feasible set is empty. Therefore, this problem has no solution. Please note this one. This problem has no solution, since the feasible region is empty or feasible set is empty. So, it is not necessary that for every LPP problem there will have some solution. I must have some feasible region which is non-empty, and then only I can obtain the solution. So, this is one case. The next, see, z equals maximize. We are in general take maximization problem. Z equals 6 x 1 plus 10 x 2 subject to 3 x 1 plus 5 x 2 less than equals 10, 5 x 1 plus 3 x 2 less than equals 15, and the non-negativity conditions, that is x 1 plus x 2 greater than equals 0. So, to find the solution, again equate the inequality constant and draw the equations as it is, as we have done earlier. So, this is x 1, this is x 2. So, there will be one line which will be crossing here, say this is 2, and somewhere here it will be there. If it is 3, it will be little above 3. So, it will be something like this. So, this is the line 3 x 1 plus 5 x 2 equals 10. The other one is 5 x 1 plus 3 x 2 equals 10. So, it will go through 3 and the point 5. So, that if you see, it will be something like this. So, here also both are less than equals. So, I am giving the direction, it is 5 x 1 plus 3 x 2, this is equals to 15. So, this is on this side. So, the feasible region is quite clear. Feasible region is this one. Extreme points are 0, A, B and C. Your point 0 is 0, 0. Your point A will be 3, 0. Point B is if you solve it 45 by 16 and 5 by 16, whereas your C will become 0 and 2. So, these are the 4 points, extreme points whatever you are obtaining. Now, at these extreme points you have to find out the value. Z at O is 0, 0, 0. At the point A its value is 18. At the point B Z equals B it is 20. At the point C the value is 20. So, the maximum value is attended at two extreme points, at the point B and at the point C. So, therefore, what happens here? It is not that there is only unique solution, there may have more than one solution, and since this is a convex set, therefore, if you join this line B and C, any point you take on B and C, that also will give you the maximum value of the objective function. Or in other sense, for this particular problem, you have infinite number of solutions, infinite number of optimum solutions. Please note this one. We have the infinite number of optimum solutions. The reasons we will discuss whenever we are going through the theory of simplex method and other things in details. So, one problem we have done earlier which has unique solution. We have done one problem which has no solution, and if you consider this particular point, this has unique, not unique, the multiple solutions, that is infinite number of optimum solutions, and at each point it gives you the optimum value. Now, graphically if you talk, graphically we can say that one LPP is unbounded. If you take graphical case, one LPP is unbounded if the feasible region is increasing indefinitely in the same direction. If the feasible region is increasing in the same direction, please note that one, in the same direction. That means, if I draw something like this and if I have something like this, for both cases the direction is on the upper side. Therefore, if you draw, the region will be increasing as you increase the values of x1 and x2. So, feasible region extends indefinitely here, increasing and in the same direction, then we say that the LPP is unbounded. Whereas, the LPP will be unbounded, LPP is bounded for, if I say LPP is bounded, again if I draw something like this and if I draw something like this, where in both cases direction is on this side, that means feasible region is like this. So, if I can draw some circle in such a fashion that the feasible region lies inside the circle, now the radius of the circle may be as large as possible, but if I can draw one circle of sufficiently large radius such that feasible region lies inside the circle, then we say that LPP is bounded. So, graphically the LPP is unbounded if the feasible region extends indefinitely in the same direction. Please note this one. It is unbounded if it moves in the same direction, whereas the LPP is bounded if we can draw a circle of sufficiently large radius such that the feasible region lies inside the circle. Therefore, we can say that the existence of solution of LPP. In general, what we can say for the existence of solution of LPP, if you have a LPP of the form Z equals AX plus BY and your feasible region is, your feasible region is suppose R. So, number 1, if R is bounded, then R has, then Z has both maximum and minimum value. Please note this one. If R is bounded, Z has both maximum value and minimum value. Here we want to say maximum and minimum means optimum minimal value. Now, if R is unbounded, whereas A, B, X and Y are all are greater than equals 0, then Z has minimum value, but no maximum value. Please note this one. If R is unbounded and A, B, X, Y is greater than equals 0, Z has minimum value, but no maximum value. And third point is, if R equals null, that is, if R is there is no feasible solution, R equals phi, in that case LPP has no solution. So, these are the cases. Depending upon the boundedness or unboundedness or empty, it will be either as a solution may be unique or infinite number of solutions. Maybe we can achieve only minimum value for maximization problem and no solution. If you consider this one, say maximize Z equals x plus 2y, subject to x plus y is greater than equals 1, x greater than equals 0, y greater than equals 0. So, if you try to draw your x plus 2y something like this, it is greater than equals 1, means the direction is this one. So, your feasible region is unbounded. Therefore, this problem has no solution. Whereas, if you take minimize Z equals x plus 2y, subject to x plus y equals, x plus y greater than equals 1, 2x plus 4y greater than equals 3, xy greater than equals 0. In this case, you will get one line something like this and you will get another line something like this. And here the feasible region, if you see both are greater than equals 1, both are greater than equals 1. So, again that means the direction of both are like this, feasible region is coming like this. But here, although the feasible region is unbounded and this is a minimization problem, therefore, at this point you can obtain the minimum value, and this is possible only because A, B, X, Y all are greater than equals 0. So, at one of these points you will get the minimum value of the objective function, but in the other cases you will not obtain this value. And the last one is LPP with unbounded solution. Please note that the value of decision variables may increase indefinitely without violating any constraint, as we have shown earlier. In that case, the value of the objective function increases indefinitely. Both the solution space and objective function becomes in that case unbounded, and unbounded solution is equivalent to infinite number of solutions, but no optimum solution. Please note this one. If the region feasible region is unbounded, you can obtain number of solutions which are satisfying the your constraints, but you will not obtain the optimum solution. The examples are given earlier. So, next the simplex method we will start in the next class.